Thank you, Sophia, for the introduction, and thank you all for joining us for this one-hour web presentation about digital oscilloscope basics. I wanted to also point out that if you wish to view this presentation in the full screen, you'll see the control in the lower left-hand corner. This presentation is a basics presentation. It is designed for people who have maybe little experience with oscilloscopes, or maybe it's been a while since you've used one. We find that oftentimes engineers are tasked with using an oscilloscope as a primary troubleshooting or design tool, but may not have formal training in conceptually and practically how to use the tool. And at the same time, an oscilloscope is one of the most ubiquitous and complex tools that may be on your bench. So the purpose of this seminar is to kind of start from ground zero and to introduce you all to the concept of an oscilloscope, what people are using them for, understanding how different oscilloscopes vary in terms of feature sets and specifications. And that'll be the front half of the presentation. After that, I'm going to try and generally classify the most common types of applications we see people using oscilloscopes for, and show you a few of these examples. Oscilloscope technology, while it's been around a long time, has also advanced a lot in the last 5 to 10 years, and modern oscilloscopes can do quite a bit more than traditional analog or digital oscilloscopes can do. So I'm going to introduce some of those more advanced features and applications to you towards the end of the presentation. And then, of course, I'll wrap it up with an introduction to the Yokogawa family of oscilloscopes at the very end. So with that, let's jump into the core of the presentation. If I were to ask you very simply in one sentence, what is an oscilloscope? If you thought about how to answer that to somebody who might not be technical or to an engineer, how would you do it? Well, if somebody asked me, I know what I would say. My answer would be, it is a graphing instrument. It's actually, more specifically, an instrument, a waveform measuring instrument that graphs or plots amplitude or voltage versus time. And depending on what you're trying to measure, the time may be a very short duration of time, milliseconds, microseconds, picoseconds, nanoseconds, and on the voltage, or it may be a longer time scale, maybe several seconds long. It may be a single shot event, or it may be a repetitive event. But nevertheless, we have a time versus amplitude, and on the amplitude side, similarly, we may be interested in monitoring small voltage changes all the way up to very large high voltage changes across that period of time. So that's a very basic idea of what they're used for. Let's take a closer look at a typical oscilloscope display. And pretty much every oscilloscope out there is going to have this type of display, and specifically, it's going to have major grid divisions, and it's going to have minor grid divisions. And on the major grid division side, you'll always see 8 divisions vertically. So if you count the squares, there'll be 8 squares from top to bottom, and there will be 10 squares or 10 divisions from left to right. And this is just kind of a historical convention that is carried through modern oscilloscopes. And that it's just a convenience thing. It just helps you very quickly look at the number of divisions to size up the amplitude or the time of the waveform you're looking at. So in this case, if you take a look at the boxed red and the boxed green values, you'll see that the oscilloscope here is currently set to 500 millivolts per division on a vertical scale. So vertically, we can count this square wave or this pulse. You can see that it has 2 divisions. It crosses 2 vertical divisions. So 2 divisions by 500 millivolts is 1 volt. So very quickly we can eyeball it and say this is a 1 volt amplitude signal. It goes from, looks like 0 because you can see the ground indicator on the far left to 1 volt. Now on the x-axis, that was the y-axis. On the x-axis, you'll see the indicator shows in the top right that the setting is 100 microseconds per division, so it's a very short window of time. for each one of the divisions. And if we count the divisions in the pulse, you'll see there's 5 divisions. So 5 by 100 microseconds means that it's a 500 microsecond or half a millisecond pulse. So that's kind of the nature of how you would interpret the display on an oscilloscope, and every oscilloscope out there, no matter who makes it, is going to have vertical controls and divisions, volts per division, and horizontal controls, which is the time per division. Now, those display indicators correspond to physical controls. And here's a look at the physical controls on the oscilloscope. You'll see there will always be a vertical section, and there will always be a horizontal section. That vertical section is going to allow you to adjust the millivolts per division, and the horizontal section will allow you to adjust the amplitude of the time per division, as well as sliding it left or right or up and down, depending on how you want to zero it out. So that's a look into the basic display of an oscilloscope. And I do want to take a minute to mention that an oscilloscope is fundamentally a time domain instrument. So, of course, there are instruments out there that measure frequency and time, and other instruments in the time domain you may use also are things like data acquisition instruments, scope quarters, or electronic recorders or chart recorders. These are all time versus amplitude type of instruments. At the same time, basic math and electrical theory tells us that any time domain signal can be represented in the frequency domain, and sometimes we're interested in analyzing the frequency content of a signal. You may use a specialized instrument such as a spectrum analyzer, a FFT, or network analyzer to look at the frequency content. And what you'll find is sometimes time domain instruments nowadays can convert these waveforms into the frequency domain and show you the frequency content to some extent as well. So I do want to point that out. Why do people use an oscilloscope? As I mentioned, we will go through some more detailed applications, but certainly these are the top 3 reasons why engineers and developers and test engineers are using oscilloscopes. Primarily, of course, they want to look at the waveform. So it may be as simple as, I just want to see if the signal is there. Maybe it's a flat signal if I have nothing, or maybe it's a clock signal. I want to see verify that there's actually a waveform there. I want to visually check the shape, make sure there's not a lot of noise, or check its behavior over time, or compare it with another waveform. Maybe you're in product test and you want to make sure that the waveform from a certain pin or certain section of your device is consistently the same across multiple batches. So that's kind of the first application. The second type of application is characterizing that waveform. It's taking the next step beyond just inspecting the waveform and taking and looking at a parametric value or a numeric value, such as what is the frequency of the signal, what is the peak-to-peak voltage of the signal, or some sort of a numeric analysis or calculation to characterize the behavior of that waveform. So those are both common, and the third very common method that people use oscilloscopes for are to find glitches or find anomalies. So as a troubleshooting during design or development, or as a maintenance and support tool, maybe you have a failure that is, whether it's intermittent failure or whether it's a reproducible failure, by using an oscilloscope attached to the device when it fails, that can give you insight into why the signals may have caused the failure, what may have triggered the sequence of events that led up to that failure. And there, of course, are things that you can do with the oscilloscope to make that type of troubleshooting a little bit easier that we'll talk about in a little bit. But those are the top 3 reasons why people are using oscilloscopes. To get a signal into the oscilloscope, in the first slide I mentioned that amplitude is usually voltage, and that's true. At the point the oscilloscope interfaces with the real world, it is going to want to read a voltage. But oftentimes you may be using an oscilloscope or want to use an oscilloscope to measure something that's not purely a voltage. And so there are a large number of transducers on the market, probes, and physical transducers that will convert other types of physical or mechanical or non-voltage type of electrical signals into something that the oscilloscope can display and analyze for you. So things like differential measurements, or maybe you have a very high kilovolt type of measurement that you can't take directly in the instrument, or maybe you have a more physical type of sensor like an accelerometer or microphone or a strain gauge. These are all things that oscilloscopes can actually look at with the right type of transducer. All right, so there are a lot of oscilloscopes on the market, dozens, in fact. While there's only 4 or 5 major manufacturers, there are certainly lots of models from every manufacturer, including Yokogawa. And so how do you determine which oscilloscope is appropriate for what you're trying to do? Certainly there's a large variance in cost and performance across manufacturers and across their product families. So I want to talk about the key differences between oscilloscopes we'll start with analog bandwidth, sample rate, memory length, those are the big 3, and then also discuss some differences in terms of waveform update rate, memory segmentation, channel types and inputs, and then of course feature set and usability. These are all factors that should influence whether or not that instrument, that type of, or that variation of oscilloscope is going to work for what you're trying to do. And just as a side note, as a little bit of trivia, you may be wondering what that oscilloscope is measuring in the bottom right-hand picture. It's actually not measuring anything at all. We had loaned the instrument to a movie set for a science fiction film, and so that's just something entertaining for you guys there. All right. In terms of bandwidth, this specification is one of the main indicators of an oscilloscope's performance. And while pretty much all oscilloscopes these days are digital, they do have analog bandwidth characteristics at the front end. So what that means is its bandwidth specification tells you what's the highest frequency component that it can, quote unquote, accurately capture. And I put quotes around accurately because the technical definition means that this bandwidth spec is the frequency at which this input signal is going to be attenuated by 3 dB. So 3 dB actually corresponds with about a 30% drop in amplitude. So in other words, if you have a 500 megahertz bandwidth instrument, like what's shown in this graph, then around 500 megahertz, you would expect a 1 volt sine wave to be of an amplitude of 0.7 volts or so. So it's important to note that the bandwidth tells you it's going to be good for frequency content measurements, but you actually start having a little bit of roll-off before the spec of the instrument, well before the spec of the instrument, if you want to maintain good accuracy. And again, keep in mind that accuracy specs on oscilloscopes are DC accuracy specs, and like an audio system or home audio system or speaker system, its amplitude accuracy is going to vary over its frequency range. So the only way to get a good look at that is by looking at a frequency versus gain plot that may be supplied by the manufacturer. Here's one that I'm showing from Yokogawa, and I'll also show one here, which is Yokogawa compared with a competitor model, which is in blue, that you'll see has some a little bit of distortion at the higher frequencies towards its specification. So just like speakers, like I say, it's important to try and maintain flat frequent amplitude performance across the frequency range. All right, so that kind of describes the front end of an oscilloscope, which influences its analog performance and how much bandwidth that will not be filtered or attenuated into the instrument. Once it gets into the instrument itself, then the instrument is going to digitize the signal using a clock. Actually, this slide is related to what I was just talking about. The front end of the instrument may attenuate that signal, or will attenuate that signal at its bandwidth spec. So if we have a 100 megahertz bandwidth signal, then we'll have a 1 volt peak-to-peak signal. At that bandwidth will be attenuated by 30%. Okay? And bandwidth is important to note because some signals have high-frequency components, especially digital signals. So while the square wave that's shown in the top half of these three images has a 1 megahertz fundamental frequency, it's going to have quite a few higher-end harmonics. So when we look at that 1 megahertz square wave with a 200 megahertz bandwidth instrument on the left, it looks as we would expect, and we can see good detail. In the middle, we've restricted the bandwidth to 20 megahertz. And in the time domain, the signal looks pretty much the same, but if you look at the frequency domain transform, you can see that there is cutoff of the higher frequency harmonics. So if we were looking in the looking for the absolute best information about the higher frequency characteristics, then we wouldn't be able to see past 20 megahertz in the second example. And then in the last example, of course, we restrict the bandwidth to 1.28 megahertz. It's still higher than the fundamental frequency of the square wave, but all the higher frequency harmonics are getting attenuated, and then we get severe distortion in the signal. So the bottom line is you want to have an oscilloscope which is going to have bandwidth that's much higher than what you will ever need. That's generally the rule of thumb. And all oscilloscopes these days will have bandwidth limiting filters, usually per channel, that can actually restrict the bandwidth and bring it down if you don't need all of it. But of course, if you need more than the oscilloscope's spec bandwidth, then you're out of luck. You need to get a higher performance model. So just like I showed you, in terms of having enough bandwidth is important, sometimes having too much of bandwidth can also be a problem. So the example I'd like to give here is, in an extreme case, imagine you're looking at a thermocouple or making a temperature measurement. Typical temperature measurement may be 1 a second or 5 times a second. But if you measured temperature at 1 million times a second, then you would see a lot of noise in that measurement. And so there is such a thing as too high of a bandwidth. And same thing is being shown here. If we have an input signal that is the same in all three, sometimes we have too much bandwidth, and that shows us a lot of display noise. And sometimes we have customers that ask us, why is your instrument so noisy? And it's not that the instrument is noisy, it's actually that the noise is present in the signal. There's a lot of high frequency display noise, and it's visible whenever your instrument is operating at its full bandwidth. So sometimes it's important to restrict the bandwidth, and sometimes it's important to have enough. It is a balance to find the right bandwidth for your application. All right, the next key spec between oscilloscopes is going to be sample rate. And we talked about the analog front end of the scope. The sample rate is going to tell you the clock frequency at which the waveform is digitized into the instrument. So the sample rates are spec'd at its maximum rate. The reality is oftentimes instruments will not run at their maximum spec rate. And I'll explain why in a second here. The key point about sampling is all instruments that are digital that sample are prone to undersampling signals. So just like you need to have enough analog bandwidth, you also need to have an adequate sample rate. So if we're trying to take a capture of the red trace, then on the top half you can see our sample rate is very high. Time between blue dots is very short, and we can accurately reproduce the signal on the right-hand side. On the bottom half, if your sample rate is low relative to the signal you're trying to measure, then you don't have enough information to accurately reproduce the signal, and you'll get the distortion or aliasing effects in the instrument. So it is important to keep an eye on the sample rate of the instrument, not only the sample rate spec of the instrument, but the actual sample rate that is being used at all times in the instrument. A related point in terms of sampling, there is something called equivalent time sampling or repetitive sampling in oscilloscopes, and this is a method by which you can use if you have a repetitive signal to effectively get a much higher sampling rate. And what this does is, over multiple acquisitions, it shifts the sample clock very slightly, and it builds over time a more detailed picture of the waveform with effectively much higher sample rate. And just as an example, the Yokogawa instrument, which is normally specified at 10 gigasamples, with this mode can go up to 2 terasamples on a repetitive signal. So sometimes if you need very high sample rates and your signal is repetitive, and keep in mind this may be an option for you, repetitive sampling mode. Okay, the third most important specification when looking at oscilloscopes is the memory length. And memory length and sample rate are related, but memory length, of course, is going to tell you how long you can continuously record or digitize a waveform. Unlike a data acquisition system, which usually runs more slowly, you can't acquire or digitize a signal indefinitely in an oscilloscope. At some point, it's going to run out of memory, and you're going to need to stop and save that waveform from its acquisition memory to a more permanent memory, and then rearm, and then reacquire. So at the sample rates that oscilloscopes run, oftentimes in the gigasamples, the memory is just not adequate to continuously stream this information to a disk, for example. So what you'll see is usually the faster an oscilloscope is spec, the less acquisition memory it has. In the past, it wasn't uncommon to see oscilloscopes with hundreds of thousands of points. Nowadays, you'll typically see oscilloscopes with a few million points of memory. And here, for example, you see 3 variants of Yokogawa family oscilloscopes that go from 6 million points per channel to 2 billion points per channel when the sample rate is lower at 100 million samples a second. As I mentioned, memory length is related to sample rate by the following equation. For a fixed observation time, memory length is equal to that observation time multiplied by the sample rate. So what that means is, if you hold the observation time the same, if your test is 1 millisecond, for example, it's fixed. If your memory length goes down, your sample rate must go down also. If your memory length goes up, then your sample rate can go up as well. So memory length can sometimes restrict your sample rate if you don't have enough of it. That's the message here. As an example of this, let's say, again, we're trying to measure the red waveform, the red trace, and we are dealing with 2 instruments. The first instrument only has 5 points of memory. Well, if you have 5 points of memory, then you have to choose to spread out those 5 points over the entire observation period, or you have to choose to use those 5 points for a shorter observation period to get the detail that you want, to get this higher sample rate. So neither situation is ideal. The best solution is to have long memory, and by having that longer memory, then you can maintain the higher sample rates across longer observation periods. That's the message here in this slide. And let's look at a couple screenshots here that actually show the effects of different memory lengths. Here you can see we have just 1,000 or 1,250 points of memory in the top half of the waveform display, and we've actually zoomed into that runt pulse in the middle. And you can see the runt pulse doesn't show us a lot of detail because, again, we only got about 1,000 points of memory allocated for this observation period. Now, same observation period, just by increasing the available memory to 1 million points, now we have allowed the sample rate to go up. So let me back up one step here. So keep in mind that this oscilloscope may be fully capable of running at much higher sample rates than what you see here. But it is, for that observation period, if you only have a limited amount of memory, it will never achieve its full sample rate. It's going to be restricted by the memory. Only by having more memory are you going to be able to reach or get closer to the full sample rate that the instrument can actually achieve. And obviously you can see there's a good amount more detail there. So memory length is important. I would argue that it's equally or more important than sample rate when you're looking at oscilloscopes. All right. Here is another slide taking a look at sample rate. And keep in mind that most oscilloscopes will show you the memory that's currently being allocated and will also show you the sample rate. I have those boxed in green as well as the time for division. So knowing the sample rate that the instrument is currently set to is going to give you an indicator if you are at risk of undersampling and having any aliasing effects. So always keep an eye on your sample rate and your memory when you're operating an oscilloscope. Okay, a few more differentiators between oscilloscope families. Another one that you see receiving quite a bit of attention in the last few years is waveform update rate. That means how fast can I update the screen, or how fast can I acquire data or waveforms, snapshots of waveforms. This little animation will show you conceptually what that means. In a scope, most of the time you'll have a trigger, and when a waveform crosses that trigger or meets that trigger condition, then it will capture a waveform for that observation period you've set. It will transfer it to memory, it will show it on the display, it will then rearm and then get ready for the next trigger. And during that time when it's rearming and waiting for the next trigger, there is a dead time or a time that this instrument is blind that will actually not see other triggers. And you'll actually see that there was a glitch in this example. There's a sine wave right there in the middle of those more square-looking waves, and we missed it because of the dead time. So the dead time spec is spec'd in, the waveform update rate is spec'd in waveforms per second, just like the sample rate is spec'd in points per second. All oscilloscopes do have dead time between acquisitions, and dead time is actually the inverse of the waveform update rate, and it is related to that specific brand and model. It's also related to memory settings and other scope settings. If you turn on analysis or math or logic in some models, it will actually slow down that acquisition rate. So just like the sample rate, manufacturers like to put the best case scenario. With waveform update rate or waveforms per second, it's the same story. You'll usually see the best case scenario. And if you take a closer look at waveform update rates, you'll see that there is variance based on what else you're doing with the oscilloscope. This graph shows waveform update rate when you're using 2 channels plus some logic plus serial bus decoding. And the Yokogawa is going to be able to have a maximum performance of 2.5 million waveforms per second, so least amount of dead time. Other models are considerably slower and will run between 10 to 100 waveform updates per second. And so you may not see it visually, it may look the same visually, but if you're looking for an anomaly or a glitch, you generally want the least amount of dead time so you have the best chance of capturing that anomaly or glitch. How do you determine the waveform update rate? Well, as I mentioned, if you look at the spec of the instrument, that will tell you the best case scenario. In reality, oscilloscopes are not running at the full specification the vast majority of the time, And the only way to get your true update rate is to look at its acquisition counter. And a lot of modern oscilloscopes will have this acquisition counter, as well as having an output trigger. And by monitoring either of these two things, then you'll get a feel for how fast the waveform is really updating. Because keep in mind, the human eye can only see about 50 frames a second, and obviously the oscilloscope is capable of running much faster than that. All right, memory segmentation is also another differentiator when it comes to oscilloscopes. We know that most oscilloscopes use PC-type displays, so maybe you're running an XGA resolution of 1024 by 768. That means you have about 1,000 pixels, display pixels, to work with. At the same time, I told you earlier that oscilloscope memory can be millions of points long. So sometimes you don't need a million points to describe your waveform when you're only going to show 1,000 points of it on the display and maybe not zoom into that waveform. So we don't need all 2 million points to describe this waveform that I'm showing here. So what do we do with that 2 million points of memory? Well, the answer is, instead of having one continuous 2 million point record, maybe you could divide that or segment that memory into 2,000 frames, like pages in a book, of 1,000 points each, 1,000 waveforms each. And that's exactly what Yokogawa models do in all of our oscilloscopes. All right, another key differentiator here with oscilloscopes is input channel types. And you'll usually know how many channels you need to measure. The vast majority of the time, you'll see 2 and 4 channel models. And if you need to work on 1 through 4 types of inputs simultaneously, you have a lot of choices available to you. At the same time, we do realize a lot of people these days are working on 3-phase measurements with inverters, with appliances, with motors, with electric vehicles, and so on. And this may require more than 4 channels. And so this is one of the reasons that Yokogawa does have an 8-channel and a 16-channel and a 128-channel model oscilloscope. So we realize that there are applications where you need to simultaneously look at all these channels and compare their behavior, and maybe you don't want to buy 4 oscilloscopes and link them together. So those are available. Keep that in mind. Okay, so we spent about half of this time covering key specifications and helping you understand conceptually what these specifications mean. Now let's talk about how you would apply the oscilloscope to take some real-world measurements. And I'm going to start with the simple one that I sort of mentioned before. We want to look at some measurements. We want to just eyeball and see what our signal looks like. In this example, we are looking at 5 seconds of a waveform from left to right. So we've got actually a relatively slower test. And usually when you're running slower tests, you'll see the waveform animate or roll from one side of the screen to the other. Now, maybe this is a startup test of a motor. Maybe it's a destructive test or something like that. Or maybe anyhow, it's a 5-second test. And then after that test is completed, we want to go in and stop it and analyze it in the instrument, maybe on the PC. And so on the bottom left and the bottom right, we see zoomed in sections where we can analyze the spike a little bit more closely, or we can analyze the noise there on the right-hand side a little bit more closely. So these are typical types of, this is one typical type of waveform observation setup that you might use on an oscilloscope. Now, obviously, eyeballing a measurement is not going to be very accurate. And fortunately, oscilloscopes have all sorts of built-in functions to automatically make measurements for you. And so these built-in functions can range from very simple type of measurements using cursors, which I'm sure all of you are familiar with, to a fully advanced analysis of parameters. And I'm just going to go through some of these and show you what those types of measurements might look like on a screen. So we'll start with the basic cursor measurement. And of course, every oscilloscope is going to have the ability to do vertical, horizontal, and a combination of vertical plus horizontal cursors. And these cursors will let you easily look at amplitude differences, time differences, and show you those deltas. What you do have to keep in mind when you're using cursors, though, is that cursor measurement is limited to the pixel resolution of your display. So if you're looking for the most accurate measurement, the cursor measurement is actually not a good way to accomplish this. It will get you in the maybe 2 to 3% accuracy range, but it's not going to go down to the actual sample unless you zoom very, very closely, tightly into the signal to take your measurement. So keep that in mind. The cursor is just a starting point for automated measurement. Another way to make your cursor measurements a little bit more reliable is by turning on basic and continuous statistics. So here we have an automatic measurement over time. Actually, here we just have a basic cursor. And then here, what we've done is automated that measurement of peak-to-peak voltage with the instrument's internal algorithm. And again, most or all oscilloscopes are going to have the ability to show you this type of measurement. Here we're actually measuring 9 different parameters: a maximum voltage, a minimum voltage, a peak-to-peak voltage, overshoot, the mean voltage, frequency, the positive cycle width, the rise time, and the fall time. So these are all typical measurements you can expect to do with the scope. And these are fully automated measurements. As you can see, these measurements are jumping around, and to get a more stable reading, what you may want to do is average those measurements or perform statistics of those measurements over time. So here we've taken 2 parameters, peak-to-peak and rise time, and over multiple acquisitions, we're looking at the average rise time, the average peak-to-peak, and getting some statistical analysis on that. This is another factor that can influence the accuracy of your measurement, and it's display partitioning. So an oscilloscope, again, is going to have a limited display in which you have to potentially look at more than one signal. And if you find yourself resizing the signal manually or repositioning them vertically on the display, it is also potentially dangerous to your measurement simply because you are actually reducing the gain if you reduce the voltage per division in order to take less of the screen. A better way to accomplish display partitioning is to go into the oscilloscope setting and let it divide the screen up for you per channel so that you can maintain the full scale input and the best accuracy on that waveform. So that's what this slide is showing. Again, regarding statistics, basic statistic measurements here we're showing statistical information over time continuously. And I mentioned advanced parameter analysis. Maybe we want to look at those measurements peak-to-peak or rise time over multiple acquisitions or on a cycle-by-cycle basis. And some more advanced oscilloscopes will allow you to do that. So you can actually go through and take a finer look at those specific measurements. In fact, these measurements can be even displayed in a histogram. So here you can see peak-to-peak measurement displayed in the bottom left histogram and a rise time in the bottom right histogram. And the histogram is useful because it tells you the distribution of this measurement. Maybe it's a Gaussian distribution like you see here. Maybe if it's a clock signal that you may be jumping between 2 or 3 frequencies, then you'll see a bimodal or trimodal distribution. So this type of analysis is potentially useful in a design type of environment. And lastly, you can also apply trending to your measurements. So if you're characterizing the waveform, maybe you want to take those measurements over time. So let's look at peak-to-peak measurement of the waveform as the circuit warms up. or as you're applying some external influence to the circuit. And a trending type of advanced display would allow you to do that. So this is all part of waveform characterization, which is one of the most common functions that people are using oscilloscopes for. And look for oscilloscopes to be able to do these things if you want to be able to extract more than just your basic measurements out of the instrument. Most oscilloscopes these days also include user-defined math. So being able to write your own equations in the instrument to create math waveforms and to create user-defined parametric calculations based on arithmetic, on trigonometry, on calculus types of functions, on pulse width measurement. This can all be done due to the advanced nature of the hardware processors in the instrument. And I had mentioned fast Fourier transforms or frequency domain view of the time domain signal. And sometimes even you may want to look at X versus Y. So rather than your conventional amplitude versus time, maybe you want to look at amplitude versus amplitude or current or versus voltage. And oscilloscopes usually do have advanced XY display modes as well. So you do have a large number of tools to do waveform characterization. So that's the first and second application. The third application that I talked about is how to find an anomaly. If you're troubleshooting, this is one of the most common things that you're going to look for. As I mentioned, keeping the dead time low is important. But beyond that, how do you locate an anomaly? And the answer to that is sort of, it depends. And in the case of this box, anomaly, if I were to say, how do you isolate this one? Anyone with oscilloscope experience would say, that's easy. I'll set a trigger level that's higher than the other periods, and I can isolate that anomaly. So that's correct. If we're looking for this type of anomaly, and I said, all right, well, how do you isolate this anomaly? The trigger level method is no longer applicable. So again, anybody with oscilloscope experience may look at that and say, well, I can set a pulse width trigger, and you'd be correct. That's also a very common method and available method to detect these types of intermittent glitches. So a pulse width trigger would separate, you'd be able to define a maximum and minimum pulse width and trigger off of that condition. But again, sometimes you don't know what your glitch is going to look like, or sometimes it may be a little bit different, difficult to describe in a trigger. So how would you set your trigger up to isolate this type of anomaly? And the answer is not clear when you look at triggers. So while it is important for your oscilloscope to have lots of triggers, in fact, the flagship Yokogawa model does have over 400 combinations of hardware triggers. Sometimes when you don't know what your anomaly looks like, you may not be able to set a specific trigger to catch it. And that's where the history memory comes in, or the memory segmentation comes in to be very useful. This slide is showing trigger position, which is also a related factor. If you are expecting to see events leading up to the trigger, then you will want to set a late trigger position. If you want to see events that happen after the trigger occur, then you may want to set an earlier trigger position. So trigger position is usually set in percentage from 0 to 100%, with 50% being the default setting in an oscilloscope. So back to isolating an unknown glitch. If you don't know what it looks like, look for an instrument that does have memory segmentation. And what that memory segmentation is going to let you do is when you see that glitch or anomaly go by on the screen, all you simply do is stop the acquisition and rewind. So that allows you to go back and say, all right, this was the trigger that I was looking for of the last 30 triggers. This is the one I was looking for. Isolate it, turn off the other triggers, and then take measurements just on that glitch. So that's where memory segmentation can be very useful. here's where you're seeing we've separated the glitch. We've actually taken a look at its timestamp among other triggers, and we're able to take some cursor measurements. All right, so those are your basic oscilloscope types of functions. As I mentioned, modern oscilloscopes have quite a few more features that are continuously being added based on user demands, and one of those is serial bus analysis. Those of you who are doing or working with any serial buses are probably aware of serial buses, the most common ones being I2C, SPI, CAN bus, LIN bus, serial bus like RS-232 or 485. Maybe you have some of these digital buses in your circuit that you want to look at on the oscilloscope and not just with a protocol analyzer. Here I have a typical CAN bus frame, and of course the CAN bus in every protocol has a definition which includes a header, a data field, and some error correction or end of frame information. And here's what a CAN bus signal would look like on your digital oscilloscope. So if I were to ask you to interpret what that means by hand or manually, it would be very tedious, if not impossible. So what manufacturers have done nowadays with their serial bus packages is, knowing that users do want to extract this information out, is we've added the ability to go in and have the oscilloscope have knowledge of that protocol that you're using. So whether it's any of those ones that I named or a user-defined protocol, it lets the oscilloscope go and decode directly under the waveform what's the address of that packet, what's the data that's being carried by that packet, and so on. So this type of analysis package, this is just to show you conceptually what it does. It can also do other things involving triggering and searching and so forth, but this is actually a 2-bus decode of an I2C bus on the top and CAN bus in the middle with a table view of both. And along the same lines, so much work these days is being done with serial buses and digital packets and digital buses that our users find that it's important to decode values, digital values, on the screen. So rather than download or decode this by hand or transfer it to Excel or MATLAB, there is some benefit in being able to directly have the instrument decode those values after you specify your bit rate and a threshold, and maybe it's a synchronous or asynchronous signal with a separate clock, or asynchronous like we have here. And having that ability, decoding it in binary or hex, that can be quite useful if you're working with digital circuits. Conversely, maybe you are working with digital circuits and you don't want to decode something, but you want to trigger off of a digital bit stream. So this is one of the most advanced type of triggers that we do offer, that Yokogawa does offer. It's a serial bit stream trigger. And that allows you to actually define a string of zeros and ones, again, clocked or unclocked, and the instrument hardware will actually wait for that string of digital bits to occur and then trigger and capture a waveform. So serial bus analysis is increasingly popular, and you'll see it in pretty much every model of Yokogawa oscilloscope as an add-on optional package. Another area that's receiving a lot of work and attention these days is energy efficiency and power measurement. So traditionally, oscilloscopes have been used to measure just voltages and physical transducers, but at the same time, we see a lot of users who are using current measuring transducers or current probes to measure the current consumption of their device, and in combination with the voltage consumption of the device, you can actually measure the power consumption in watts or watt hours and so forth. So modern oscilloscopes with a power analysis package do allow you to take a closer look at things like power consumption, power factor, power quality, and whether that's on the design cycle or design side or test side or service side, that's actually quite useful. Yokogawa happens to be the world leader in electrical power meters, power measuring instruments, for the highest accuracy, but certainly with an oscilloscope you can get in the ballpark to get a feel for how much power your device may be consuming or its efficiency. We know that there's a lot of work being done in energy efficient devices, and so this is an important part of where user applications are going as well. I mentioned that with serial bus signals, a lot of it is related to the digital work that customers are doing. At the same time, maybe you don't have a serial bus, maybe you have a parallel bus. And we know that pretty much all modern electronics use digital components. So why should you restrict yourself to just taking analog measurements on your instrument? And that's the nature of what you see on the market called mixed signal oscilloscopes. So a mixed signal oscilloscope means that not only can you look at the analog side of an instrument, but you can look at it in combination with the digital side or digital bits of the instrument. So a mixed signal instrument will allow you to look at some logic and some analog inputs in combination. In addition, there will be dedicated measurements to those logic inputs, things like duty cycle and frequency of the logic bits, being able to potentially even convert those logic bits using a virtual B to A function and so forth. Think of it as a simple low-end logic analyzer that's built into your oscilloscope. So a mixed signal instrument, mixed signal oscilloscope would allow you to do things like that. Traditionally, when people are working with logical types of signals, you may be reaching for a logic analyzer or protocol analyzer. A mixed signal instrument, a typical one from Yokogawa, would have 4 analog channels and either 16 or 32 logic bits, plus the ability to do serial bus triggering and decode. And the key here is, rather than having 3 separate instruments to look at your analog signals, then look at your digital signals, then look at your serial bus signals, you can have it all in one instrument and correlate those measurements on the same time axis. So this is a display. It looks a little bit complex at first, but keep in mind, I've got it separated for you here. You have a yellow analog voltage or waveform. We have some blue digital or logic bits, and then we have a serial bus which is being decoded, which is the green trace. And all of these may be part of the same engine control unit in a vehicle or aircraft or some kind of circuit board. And the ability to see these all in one instrument is a relatively new phenomenon in the oscilloscope industry. Okay, the last application here is, this is very cutting edge, but I do want to show it to you, because if you haven't looked at oscilloscopes, newer models in the last couple of years, this will be new to you, and that is signal enhancement and noise reduction. So you don't typically think of using an oscilloscope for cleaning up the signal, but in fact, modern oscilloscopes do have quite a bit of signal manipulation and math and filtering capability inside of them. And there are lots of tools you can use to clean up the signal, and once the signal is cleaned up, you can see more detail in them that may have been hidden from you before. So keeping in mind that the oscilloscope's time-based accuracy is very, very fine. It's very good on the time axis, but the voltage resolution is actually typically very poor. It's only 8 bits. How do we enhance that vertical resolution? We talked about some of the ways, using display separation, display partitioning. That's one way to do it. Optimizing the bandwidth by reducing the bandwidth to restrict the display noise. That's another way to accomplish this. There's also 3 other ways I'd like to share with you. High resolution mode is an advanced feature of modern oscilloscopes that is essentially a high-speed FIR filter that effectively gives you 12 to 13 bits of resolution on an 8-bit A to D converter. And it does this by trading off the bandwidth. So it reduces the bandwidth somewhat, but it gives you higher voltage resolution. Real-time user-defined filters using DSPs are sometimes available as well. And then if you have a repetitive signal, averaging can help clean up the signal even further. So let's take a look at a real-world example. This is just a simple clock signal. And I have the two zoom windows turned on. I have one zoom window looking at, on the bottom right-hand side, just one cycle of this clock signal. And then on the bottom left-hand side, I've zoomed in to the top, or the noisy part, of several cycles of this clock signal. And indeed, you can see that it is very noisy. We're running at full bandwidth. And if you look at the zoomed-in portion on the bottom left, you do see some banding. So that banding shows you almost like different areas of intensity. That banding actually corresponds to quantization noise. So each of those bands is exactly one LSD or one quanta of the 256 steps that are available in an 8-bit converter. So that's the typical resolution that you'll see in an 8-bit scope from any manufacturer. So how do we clean that up? The first step that I'm going to do is turn on a bandwidth filter. So I've gone from a full 500 megahertz bandwidth down to 20 megahertz. And certainly that did remove a lot of the display noise, but we still see banding. The next step I'm going to do is to turn on the high resolution mode, which is a trade-off again of the bandwidth, which we're not using all of it anyway, so no problem. And you can see that the banding has disappeared because we've gone from an 8-bit effectively to about 12 bits effectively in this example. So we're starting to get a cleaner picture of it. As it turns out, this is a repetitive signal, so we can turn on averaging. If we turn on averaging, then something interesting happens. We can start to see a spike and some overshoot there of each pulse. And that's something that was not visible before, but it is characteristic if you average everything out and reduce the noise. So having the ability to manipulate your signal and the way that you look at it through filtering, through averaging, through high resolution mode can be useful. So I just wanted to mention that to you guys as well. Last application is automated testing. Obviously, traditional oscilloscopes are used on the bench. Most of the time, we see a lot of button pushing and interactive use, but usually those tests, those manual tests, will translate into automated tests during the design validation and manufacturing cycles. And to do that, you'll want to have software tools that allow virtual control of the instrument and software drivers. So these are some of the programming interfaces that we see most commonly used. LabVIEW and LabWindows, of course, Visual Basic and Visual C, and MATLAB. Those are the most common ones. And people nowadays are communicating mostly through USB or Ethernet as compared to conventional methods like TPID or serial. As part of automated testing, some oscilloscopes will also include go, no-go, pass-fail, built-in pass-fail testing, and the ability to create masks, and these are things that are oriented more towards the automated test rather than the manual test. So we covered a lot superficially within the last hour. I do want to wrap up here with a quick overview of the families of oscilloscopes from Yokogawa that range from 20 megahertz bandwidth through 1.5 gigahertz bandwidth. You'll see the three key specifications we talked about: bandwidth, sample rate, and memory length reflected here in this chart, as well as update rate, memory segmentation, or history memory, as Yokogawa calls it, input channels, and vertical resolution. So these are all kind of important factors that will tell you if this instrument is suitable for what you're trying to measure, whether it's more of a mechatronic, lower speed application, or more of a device characterization, higher speed application. Our flagship model here is the DLM6000 Series. It's up to 32 logic bits and 4 channels. It does have the 6.25 million points per channel, and very, very high waveform update rate for troubleshooting, looking for glitches. This is the 8-channel DL7400 Series. that allows 8 analog inputs plus 16 bits of logic. And then this is our compact, low-cost, high-performance benchtop model called the DLM2000, which has something called a flex MSO channel. What that allows you to do is convert the fourth channel to 8 bits of logic input when you need it, or if you don't need it, it becomes an analog input. So basically, for the price of a DSO, you have an 8-bit MSO. It can be 3 plus 8 or 4 plus 0, your choice. It is available in 200, 350, and 500 megahertz flavors. And then, as I mentioned, the scope quarter is designed for mechatronics. It is a modular interface, so depending on what kind of mechatronic signal you want to measure, then you would swap out its input type of module. And these are quite popular in all areas of electromechanical design and test. So hopefully in this time, we've been able to kind of get you thinking about conceptually what oscilloscopes are being used for, how they differ in key specifications, help you think about maybe how you can use an oscilloscope in a way that you haven't thought of before, and share with you some of the latest Yokogawa oscilloscopes. I thank you again for your time, and hope to see you on a future webinar.
Thank you, Joseph, for a wonderful presentation. We have run out of time for our Q&A section. Please be assured that if you submit a question, they will be answered via email. Also, if you have not yet answered the poll questions, I request you to please do so at this time. I would also like to mention that this seminar was recorded and will be available for replaying in archive form 24 to 48 hours under the Technical Library on our webpage. Thank you once again, and we hope to see you online at our future web seminars.